Your phone runs AI without touching a server. A $35 Raspberry Pi can detect faces faster than most 2018 cloud APIs. Factory sensors are making real-time decisions without internet. This is Edge AI, and it's already everywhere. Welcome to AmTalk Soft. Today I'm breaking down Edge AI, what it is, why it matters, and how you can actually build with it. Here's the core idea: AI doesn't have to live in the cloud. When you run a model directly on the device where data is generated, a phone, a sensor, a robot, that's Edge AI. And it changes everything about what AI can do. Instead of sending data to a server, waiting for a response, and getting results back, you get inference in milliseconds, right where it's needed. No internet required. No round-trip latency. No data leaving the device. We're going to cover why Edge AI is exploding right now, what hardware you can run it on, how developers actually build for Edge, and what real applications look like in production. Let's go. To understand why Edge AI matters, you need to understand the fundamental problem with cloud AI: latency. When you send data to the cloud for inference, here's what happens. Your device captures the data, an image, a sensor reading, a sound. It compresses and transmits that data over a network. The cloud server receives it, runs the model, computes a result, then sends that result back. Your device receives it and acts. That round trip takes 100 to 500 milliseconds in good conditions. Under load, on mobile networks, or in regions with poor connectivity, it can be seconds. For most applications, that's fine, but consider autonomous vehicles. They need to react to obstacles in under 50 milliseconds. Industrial robots making precision cuts, medical devices monitoring vital signs, agricultural drones detecting crop disease in real time. These applications can't afford cloud latency. They also can't afford connectivity dependency. What happens when the network drops? Edge AI solves both problems by moving the computation to the device itself. The result comes back in 5 to 20 milliseconds with zero network dependency. Edge AI isn't one thing, it's a spectrum. There are 3 main tiers, and understanding them helps you pick the right approach. Tier 1 is endpoint devices, the smallest, cheapest, most constrained hardware. Microcontrollers, sensors, and embedded systems. Think Arduino, Raspberry Pi Pico, or a tiny sensor in a factory machine. These devices have kilobytes of RAM, run on milliwatts, and cost under $5. AI on these devices means TinyML, highly compressed, quantized models running basic classification or anomaly detection. Tier 2 is edge servers, more powerful systems deployed locally, not in the cloud. A server at a hospital, a gaming edge node, or a computer at a smart manufacturing plant. These might have a dedicated GPU or NPU, a neural processing unit, and can run mid-size models with full accuracy. Tier 3 is near-edge devices, smartphones, tablets, modern laptops. These have dedicated AI accelerators built in. Apple's Neural Engine, Qualcomm's Hexagon DSP, Google's Tensor chip in Pixel phones. These can run large language models locally. We're talking 7 billion parameter models running entirely on your phone. What changed to make Edge AI practical? Specialized hardware. For years, running AI locally meant running it on a general-purpose CPU, slow and power-hungry. That's changed dramatically. The Raspberry Pi 5 can run image classification models in real time, not because it got faster CPUs, but because you can pair it with a Google Coral USB accelerator, which adds a dedicated TPU, tensor processing unit, for $8. It adds 4 trillion operations per second to a $35 device. NVIDIA's Jetson Orin is the serious edge AI platform. It packs up to 275 TOPS, runs the full CUDA software stack, and handles computer vision, natural language, and robotics workloads. It's what powers most serious industrial and robotics deployments today. On the mobile side, Apple Silicon's neural engine runs 38 trillion operations per second on a MacBook. Every iPhone since the X has had a dedicated neural engine. This is why on-device Siri, real-time photo enhancements, and now on-device small language models work without a server. Qualcomm Snapdragon chips power most Android phones and include the Hexagon NPU. The Snapdragon 8 Gen 3 can run 7 billion parameter LLMs on device. Google's Tensor G4 chip in Pixel phones is specifically designed for on-device speech and image models. The hardware is there. The question now is software. Getting a model to the edge requires a specific workflow. You can't just take a PyTorch model and drop it on a Raspberry Pi. You need to go through the edge deployment pipeline. Step 1. Export to an interchange format. ONNX, Open Neural Network Exchange, is the standard. You train your model in PyTorch or TensorFlow, then export it to ONNX. ONNX is hardware agnostic, so the same exported model can run on CPUs, GPUs, NPUs, and TPUs with the right runtime. Step 2. Optimize and quantize. Full precision models use 32-bit floating point, too heavy for edge. Quantization converts weights to 8-bit integers or even 4-bit. This cuts model size by 4x and inference time by 4x, with minimal accuracy loss for most tasks. Tools like ONNX Runtime, TensorRT, and TensorFlow Lite do this automatically. Step 3. Select a runtime. ONNX Runtime is the universal choice. It handles hardware acceleration across all major platforms. TensorFlow Lite targets mobile and microcontrollers. TensorRT from NVIDIA maximizes throughput on Jetson devices. Core ML is Apple's on-device runtime. Step 4. Deploy and monitor. Edge models need to be updated over the air, since you can't physically access every device. Frameworks like Baelna, AWS Greengrass, and Azure IoT Edge handle deployment, monitoring, and model updates at scale. TinyML is the extreme end of edge AI, running neural networks on microcontrollers with kilobytes of RAM, costing pennies. The canonical example is keyword spotting, detecting Hey Siri or OK Google before the full AI system wakes up. This runs on a dedicated, tiny chip consuming under 1 milliwatt. That chip listens continuously, all day, on a battery that lasts a year. TensorFlow Lite for microcontrollers and Edge Impulse are the primary tools. Edge Impulse is particularly impressive. It lets you capture sensor data, label it, train a model in the cloud, and deploy it to an Arduino, Raspberry Pi Pico, or STM32 board in minutes. No ML expertise required. TinyML applications include gesture recognition in wearables, vibration anomaly detection in industrial machines, air quality monitoring, and fall detection in medical devices. All running on devices you'd barely notice are there. Let's talk about what Edge AI actually looks like in production today. In retail, Amazon uses computer vision at the shelf level. Cameras on retail displays detect when products are misplaced, running model inference on embedded chips in the display hardware itself. No cloud. Planogram compliance checked continuously, store staff alerted in real time. In manufacturing, every major auto plant now runs defect detection on the production line. A camera at each assembly station runs a vision model that flags scratches, misalignments, and missing components in milliseconds. BMW and Toyota both have these systems in production. A cloud-based system would be too slow. The line moves at 60 cars per hour. In healthcare, continuous glucose monitors and ECG patches now run anomaly detection locally. The device detects arrhythmias and alerts the patient without sending raw heart data to any server. Privacy preserved, latency eliminated. In agriculture, John Deere's See and Spray system uses computer vision cameras on sprayers to distinguish crop from weed at 12 miles per hour. The model runs entirely on board. It has reduced herbicide use by 77% in trials. In consumer devices, every photo you take on a modern phone is processed by a local AI pipeline. Scene detection, HDR adjustment, noise reduction, portrait mode depth estimation. Apple's Core ML runs over 30 models sequentially in under 100 milliseconds. If you want to build edge AI applications, here's the practical path. Start with ONNX runtime. It's the most portable option. Export any PyTorch or TensorFlow model to ONNX, then run it with ONNX runtime on any device, including Raspberry Pi, Jetson, Windows, and Mac. The API is 3 lines of Python. For mobile, use Core ML on iOS or TensorFlow Lite on Android. Both have official converters from PyTorch and ONNX. You can integrate on-device inference into a native app or React Native in an afternoon. For microcontrollers, Edge Impulse is the fastest path. It handles the full pipeline data collection, training, quantization, and deployment through a browser-based interface. The key design principle for Edge AI, model size is everything. Start with a model under 10 MB. Quantize it. Test on your target hardware early. The performance profile on a Jetson and a Raspberry Pi are dramatically different. Don't assume, measure. Here's what to take away. Edge AI runs models on device, no cloud required. The benefits are lower latency, offline capability, and better privacy. There are 3 tiers: microcontrollers for TinyML, edge servers for industrial workloads, and near-edge devices like phones and laptops for full models. Specialized hardware, NPUs, TPUs, neural engines, is what made this practical. Every modern phone and laptop has dedicated AI acceleration. ONNX is the standard interchange format. ONNX runtime, TensorFlow Lite, TensorRT, and Core ML are the deployment runtimes. Real applications are running now in retail, manufacturing, healthcare, agriculture, and every phone in your pocket. If this was useful, subscribe. We cover AI, cloud, and software engineering every week. Next up, we're going into serverless computing too, what's changed, when it beats containers, and when it doesn't. See you there.